โอเคเดี๋ยวเราจะเรียนอันนี้แบบอย่างเร็วนะครับถ้าไม่ทันไปดูคลิปได้นะครับ we'll go really quick because we only have roughly 20 minutes left I'll try to finish this but if I can't then next Monday we'll talk about it okay alright so let's talk about linear functions okay so when you think about functions so what exactly is a function so a function is when you write code, right? Function is like you put in some input and you get the output, right? So that's how you look at it in terms of like coding and programming. Right? So you have a function and you put in some input and you get the outputs of it. Okay. Mathematically, you can think of it like that, exactly like that. You have two sets, okay, and this function f just map some of the input like input into some of the output, right? So this is like function in terms of math, okay? Function in programming might when you give the same input to the function you might not get the same output out of that function because like in programming maybe there's some side effect or whatever. But in math, when you have function, same input maps to the same output. Okay. If you put 1 into f, you get 7. You put 1 into f again, you also get 7. You won't get anything else. That's the kind of thing that we talk about here. Okay. So given a function, we say that this function is linear. Okay. So it's a function f where the input. So this notation. Let me give you a review. Okay, we refer to this as the domain and we refer to this as a range. So basically we have two sets V and W. They are both vector space. So when you think about, again, when we talk about vector space, it's like the set of all vectors that we are concerned. Okay, so if we have a vector space V and we have vector space W, we might have a function f that maps vectors between these two sets. Okay, so when I write this f colon this set to that set, so this is like the input, the set of all possible input, and this is the output. The output has to be inside W. It might not include the entire everything inside W. Okay, but the input is like you should be able to put everything inside V into f. Okay, so we say that this function is linear. Okay, this one is linear if two of these property holds. First of all, if you multiply the input, let's look at the second constraint first. If you multiply the input by alpha, the output will change by alpha as well. So that's the linear part. Like, so if you increase the input by twice, the output will be increased by twice as well. Okay, so it's like proportionally the same thing. Okay, if you multiply f with alpha, the output change by alpha. Also, if you add two vectors, the output is like exactly like when you take the output and add them later. So you can add the input first and put it into the function, or you can just apply the function separately and add the output. Okay. So if you can do these two things, we know that this function is linear. Okay. There are so many functions. There are like a bunch of like family of functions that are linear. Like everything will be linear in our work. Okay. For example, neural network. In neural network, you have a set of like input neurons, okay, and then you have like a bunch of output neurons, and then they are connected. Okay, and you have weights on this, right? Wij. Okay, and you have so you have input x1, x2, and so on. and you have output y1, y2, and so on. You have weights, and you have formula that says like y1 equals sum of w 1i times xi, I equal to 1 to power 2n, maybe it would be xn, okay, and so on. So this is like the one layer of a neural network. But actually in the neural network you need another activation function here, like do some nonlinear thing. But if you just ignore this activation function, usually it look like that, okay? It's a linear function, okay? So you can write this as you can think of this as a vector x, and this is also a vector y. You write y equals, and this will be represented. This can be represented as a matrix. So it will be some weight times x, and this is linear. The fact that it is linear because if you have some alpha, okay, you multiply x with alpha times w, but this is like alpha times w times x, right? So this is like exactly like alpha y. So if you multiply x with alpha, the output will be alpha times the original output. And if you take two input, x1 plus x2, and then you multiply by this matrix. So this matrix will be x1, x2, right? So so exactly like this is the output, right? So the output before, you can add the input and then pass it to the function, or you can compute the output separately and add, and it get to the same thing. So this means like this operation, this is the linear operations. Okay. You can do anything, some other thing like PageRank, compute. Okay. The other thing that you can get as a linear function is to do matrix multiplications. Okay, if you have vectors and then you do matrix multiplication, that's exactly what we did in one layer of the neural network without the activation functions. So given a matrix, we can view it as a function. Okay, so basically this matrix M, just take x, you can think of it as a function, right? So you have a vector x and matrix M. After you multiply x with M, you get some output. So the matrix M itself, okay, just ignore, like just forget about all the numbers inside the matrix, but think of the matrix as a whole thing. It's like this matrix just take a vector, okay, and then produce another vectors. So it's a function, okay. And when you think of it this way, this function f defined by matrix M is linear, okay, because if you add two inputs and then put into the function, it's basically exactly the same as you take the input to the function and then separately and then add it after. And also if you scale the input by alpha, the output scale by alpha as well. So when you have these two properties, the function is linear. So when you do matrix vector multiplications, it's a linear function. On the other hand, this is the key point. On the other hand, if you have any linear function, you can represent it as a matrix as well. So two way around, okay? If you have a matrix, you can view a matrix multiplication as a linear functions. But for any linear function, any possible linear functions, okay, you can find a matrix that perform exactly like that functions. Okay, so this is like pretty crazy. Okay, so given a matrix, it's a linear function. That's easy. But if you take any linear function, if you have a function that is linear, you can find a matrix that represent exactly that function. Okay, can be proved pretty easily, but I'll skip. Okay, now. So this is the key takeaway, okay? So you have a function M, Okay, we have a matrix M. Okay, you can think of M as a matrix, right? But you can think of M as a function. So you have some input space and output space. So you have a vector x. When you multiply x with M, you have the output. So M map, M is like you take another vector x1, map it to mx1, take another vector x2, map it into another vector mx2. So M is basically represent a function. Okay, but how does this structure look like? Okay, I'll put everything in terms of like the row space and column space and everything that we looked at previously. Okay, so we have M, we have the input x. Okay, so let's say M is gonna be M times n matrix. So you have M rows, n columns. Okay, so the vector x that can be multiplied with M. What's the dimension of x? So when we do matrix multiplication, we take n guys here, multiply with that, right? So x has to be in size r to the n. Okay, so the input into M is going to be r to the n. Okay, we'll look at that. We'll look inside that later. Okay, now when you multiply M with M, what's the output? Okay, the output of the matrix multiplication will be some vector, right? But this vector has M rows, right? Because one row of this produces one number in the output. Okay, so the output will be inside r to the m. Okay, the output will be r to the m. Okay, r to the m. So that's the whole thing. Okay, that's we get r to the n and r to the m from the size of the vectors. So this input vector is of size n, then the input belongs to the r to the n, and the output has m elements, so the output will be r to the m. But the question is, can you get to the whole r to the m? Can you get, like, look at one vector inside r to the m? Is there any input inside here to take that get mapped to that vectors? Is every vector got mapped by someone? So that's the question. Okay. เดี๋ยวจะดูว่าตอนนี้เราเป็นภาพรวมแล้วเราดูขนาดของเวกเตอร์แล้วเราจะได้ภาพหน้าตาแบบนี้คำถามคือทุกเวกเตอร์ในนี้มันมีคนจิ้มไปหามันได้หมดไหม Okay. Can we map to everyone in here? Depends. Okay. So what are the things that you get when you do matrix multiplications? When you do mx, when you do mx, m times x. One way to look at this is like when you do this is matrix vector multiplications. Okay. So the idea is like when you do matrix vector multiplications, you can think of it as x1, x2, and so on, right? So this will be x1 times the first column, and x2 times the second column, c1, c2, right? So matrix vector multiplication is like a linear combination of the columns of the matrix. Okay, so the all possible output of these matrix multiplications, like you take every vectors and you do the matrix multiplication, give you something, right? It will lie inside this set. Okay, because we know that all the output of M will be a linear combination of the columns of M. What is the set of all linear combination of the columns of M? What do we call this set? all linear combination of the columns of M. What kind of space is that? It's a column space. Okay, so we get to the column space of M. Okay, so we take the whole thing here, it got mapped into the column space of M. What outside here is something that you cannot reach. You cannot get to the outside because this is all you have. Okay. What else can we say about this? Okay, what else can we say about this? On the other hand, there are a set of vectors, the input, inside the input here, that got mapped to 0. So like all the vectors in here, after you multiply with M, get to 0. So I will draw it this way. Like they got mapped to 0. So this is the column space. But there are a bunch of vectors that, like this set that got mapped to 0. What is this set? This set is something, right? So this is like set of x such that mx equals 0. What is this set? We know the name of this set. Null space. It's the null space. Null space of M. But what's outside here? And what's outside there? That we have four spaces, right? Okay, but I cannot write it this way. Okay, this is one way to look at it. But let me write it in another way, really quickly. Okay, so you have a null space. It's a subspace, so I draw it as a plane. Okay, so this is a null space. Null space of M. Okay, and everything of this. So you have the whole thing, right? And the whole thing of this, the whole null space, got mapped to 0. So this is R to the N, R to the M. And this is 0. Okay, so the whole null space, so you map with M, right? So the whole null space mapped to 0. Everything else, okay, everything else here, this is also, there's a subset of this space that are, orthogonal, ตั้งฉาก orthogonal to this, okay, and this set, okay. So this is what is left. So some of the vectors belongs to this null space. Okay, the vector the vector that are orthogonal to this null space, not belonging to this, is in this set. That's the leftover vectors. We can think of this way. So if you have a null space as a plane, and you have another vectors, you can split this vector into two components. One belongs to the null space, the other belongs to some other space. Okay, what is exactly this space? So this is the row space. This is null space. This will be a row space. This will be a row space. So the row space, when you apply the metric multiplications, it will give you the column space. So this is a set of all possible output of our functions. Okay, it basically map the row space into the column space. Okay, and the null space got mapped to 0. And exactly what is left here, you can guess. It's the left This is the left null space. This is something that you cannot get from the matrix. You cannot multiply anything and get to this. Okay, so that's the pictures. So you map. So all the null space map to 0. All the row space and now column space get mapped. And this is like one-to-one mapping. So like one-to-one. Because you view this as, so the dimension of this, this dimension equals R, this dimension is also R. So it's like R dimensional space got mapped one-to-one into the another R dimensional space. The null space got mapped to 0. So this is n dimension n minus R got mapped to 0. And this is a leftover space that you cannot reach. So this dimension m minus R. Okay. So this is like the whole structure of arithmetic multiplication and also linear functions as well. Yeah. Now, if you look at this in terms of like neural network, so let me try to finish with this. If you think of this in terms of neural network, okay, so this is like, suppose you have neural network, okay, and so this is like the set of all meaningful input, and this space is like whatever you do in here, it does not see it. Okay, so if you have a neural network that you know categorize image, this is like the noise inside here is like, it will be something that the neural network won't be able to see. Okay, like when you do like the neural network is basically try to compress the dimension from one space to another. Okay, and this is like the output that you get. Okay, but thing inside the null space to be like invisible to the neural network. Okay. All right. So let me just end with that. Okay. We'll see more examples. I'll try to bring some more examples so that you can see. But this is like the whole idea of like when you do matrix multiplication, this is the structure of it. Okay. All right.